Welcome back guys for the UGC program on laser physics under Swayam portal. We have been saying all along that laser is a coherent light. It's a special type of light. What's coherence? I have explained so many times. Coherence means this particular light should have a single wavelength, single direction and should have a proper phase at every moment of time and every space point. All put together only we call it as a coherent light. All these put together make coherent properties for the laser. But the coherence property comes mostly because of laser resonating. Now perhaps you must recall that I have been telling you there are a variety of lasers. All of them can be put into three components. What I am trying to bring to your mind is any laser will have three components. There should be some medium contained in some kind of chamber. That's the first thing. Secondly, it should be pumped by electrical discharge or optical excitation or by any other means. This is the pump. And then the whole medium, gas, liquid or solid, should be kept between a resonator cavity. Only then it will become a laser, only then the light that comes out is coherent. Now what we are going to do in this lecture is we are going to look at the properties of laser resonators which bring about coherence to the laser. So we will concentrate mostly on this particular aspect. Now I bring back to your memory that look at this diagram. You have on the left side a typical representation of schematic. You have a gain medium, a laser pumping, and then you have plane parallel mirrors facing each other. On the left side you have a highly reflecting mirror. We say it is reflecting 100%. On the other hand, on the right side you have another mirror which is partially reflecting, which means it may be reflecting 50%, 60%, 90%, 98% depending upon the medium. Where it should be 90%, where it should be 98%, where it should be 50%. All these we have already explained in the earlier lecture. It depends on the gain of particular medium. Generally we say it should be R1, R2, R1 total reflecting mirror has reflectivity 100, which means if 100 photons fall on it, 100 photons will be reflected back. They will be fed back into the gain medium. On the other hand, in a partial reflecting mirror, it will be usually 95%, so that 5% of the light that comes out is a useful output for our purpose. This is represented by the second, the schematic on the right hand side. All these you have already seen, so we will go to the next step. Now there are three types of lasers: continuous wave lasers, pulse lasers and ultra fast lasers. We at the beginning we were all classifying lasers only into two: pulse laser, continuous wave laser, because it was the pulse laser means it will be about usually pulses of 10 pulse per second or sometimes 100 pulse per second or sometimes 1 pulse per second. That is how the pulse, each it will come like a bullet by bullet. The pulse width will be usually of the order of few microseconds. That is the beginning, let us say 1960 to 1970, that is beginning stage. Later the technology developed so fast that we were able to produce nanosecond pulses, picosecond pulses, femtosecond pulses and even attosecond pulses. picosecond pulse means it is a pulse, the duration of laser pulse will be 10 power minus 12 seconds. It's extremely small, extremely small time width. It is capable, such a pulse is capable of following a very fast event. Later, after a few lectures, I will go into the applications of laser. At those times, I would elaborate what are applications where picosecond lasers are very important, where nanosecond lasers are important. Right now, at this point of time, we need to know there are three types of laser: continuous wave laser like a helium-ion laser, which I will again subsequently I will explain, or pulse laser like a neodymium laser or ruby laser, and ultra fast laser like a picosecond dye laser. These are the three types. Now, we have been saying that there are variety of lasers like ultraviolet lasers, visible lasers, infrared lasers, so much of them. So, there are so many wavelengths of laser. Now, which laser works in which wavelength depends. Firstly, it is defined mostly by the medium. That depends upon the characteristic of the medium. And then, very often, like argon ion laser, you can have a multi-wavelength laser. What I am trying to bring back to your memory, which I have already explained, is an argon ion laser will simultaneously produce laser at 2 or 3 wavelengths, blue and blue-green. It will automatically, don't do anything, just switch on. If everything is okay, pumping is right, mirror is right, if you put 2 good quality mirrors, it will produce laser in 2 wavelengths. In that condition, if you want to select only one wavelength, what we usually do, we put a wavelength selective medium. The simplest one is a grating or a prism. If I put a prism, the prism will separate out blue and green at 2 different angles. Then I can put the mirror at this point, I will get a blue laser, at this point I will get a green laser. That's all what we do. In that way, I can choose a particular wavelength from a multi-wavelength laser. That's the first way. Second one, even in a laser where only one wavelength will be produced, for example, CO2 laser, this will produce laser most often, not always. It will produce laser at 10,600 nanometer or 10.6 micron. This is the far infrared laser. This will produce a very focused heat beam, heat spot. Remember, CO2 laser is not like a diode laser or a helium-ion laser. Don't ever put your hand across a CO2 laser, and fortunately, and most importantly, you cannot see the CO2 laser. It is a far infrared. This particular kind of laser can easily produce a power of 1 watt, CW 1 watt. That means continuous wave at 10,600 nanometer with the power of 1 watt, which will burn. If you put your hand in a CO2 laser, you will see the smell of your skin, smell of your tissue. It is so powerful. Not only that, there are high power lasers, CW, high power laser, capable of producing 1 kilowatt, 5 kilowatt power. They will just cut this table into 2. As you keep watching, it will cut into 2 pieces separated. So powerful lasers are available these days, and they have specialized industrial applications. We will go to these details later. Another important laser is a neodymium laser, about which I have already explained. This has a wavelength of 1064 nanometer. Why we have given 2 examples is, There is an infrared laser, far infrared laser at 10,600 nanometer, and there is another laser only 1064 nanometer. Now, let us focus on one particular laser, let us say CO2 laser or neodimag laser. Even in once you have chosen a particular wavelength, even in one particular laser, it will have certain spread width, spectral width, or that is what is called line width. Now, if you want to have a very narrow line width, if you want to have a very narrow frequency, that means you have selected a particular frequency, very pure. If you want to have a pure something, you have to select, you will get very little power. But in spite of very little power, if you want to have extremely extremely pure coffee or a pure laser, you have to filter it so many times. The same way, you can put certain types of filters or frequency selective technique to make laser of wavelength extremely small. Now, we are going to see how to do that. How do we get very narrow line width or extremely pure laser? For this, let us go back what you must have studied in your high school or in the pre-university level. You must have seen this kind of Meldays experiment, where you will have one side a metal, another side another metal, in between a string, ordinary thread will be tied up. So, the thread will be tied up and then it will be made taut. Under that condition, when there is a taut wire, you try to pluck it somewhere, then the wave will start from one end, go to the other end, get reflected. When it gets reflected, there will be a change in the phase, it will come back like this one. So, it will make one full loop with 2 points antinodes and with 2 points nodes and in between antinode. Node is a point of minimum vibration or no vibration. Antinode is the point of maximum vibration. As you can see in this diagram in number 1, you see there is one loop with only one maximum in the middle. This is called the fundamental mode. Next one, the same wire, it can be made to vibrate in the second fashion like this one. It depends on the vibration that we give to the wire, we give to the string. You can have two half length, two nodes, so two antinodes in between. The third one you will have 3 antinodes. In the fourth one you can have 4 antinodes. Like that you can keep on producing different mode pattern. One particular stationary wave pattern is called the mode. In this case, it has been shown 6 such modes. If you look at carefully, this is a node, this is a node, in between you have an antinode. So, this corresponds to 1/2 wavelength. The length of this one is just half wavelength. If you think that the total length of the wire is L, you can immediately see n lambda by 2, n/2 lambda will be equal to the total length of the wire, where L is the total length and n represents the mode number. Going back to this one, in the first one n will be 1, in the sixth one 6 will be n will be 6, because in sixth one you have 6/2 lambdas. That is the meaning of this one. Each one represents a particular mode and particular frequency. That means in a wire of 1 meter you can generate 1 mode, 2 mode, 10 mode, 100 modes depending upon your excitation. This is true for a wave on the wire, and this is true for sound wave, this is true for the wave that you see in the sea. In the sea, you have waves coming one over another. They are keep on coming. In a similar fashion, this is true for the waves or the music or the frequency produced either on veena or in guitar. Veena or a guitar, both are stringed instrument producing melodious music. The melodious music is just a combination of certain number of frequencies carefully modulated so that it gives a pleasant music to your ears. That's all. From physics point of view, you choose certain number of frequencies, certain set of frequencies, mix them together to make it very pleasant or very happy. You feel happy on listening to this one. This is for the veena or guitar. Keep this in mind. Go to laser cavity now. In the laser, you have the same thing. You have got two mirrors, 100% reflecting mirror, 95% reflecting mirror. These two act as two nodes. In between, you can have hundreds and thousands of nodes because the distance between the two mirrors will be of the order of, let us say, 1 meter. But the wavelength of light is about 500 nanometer. You see the big difference. This is 1 meter and this is 500 nanometer, which means the above condition n lambda by 2 equal to L will be satisfied for a large number of value of n. That means in a laser cavity, you will have enormous number of modes competing together to produce certain frequencies. That is the first point. Next one. All this I have explained. Here is a simple example I have chosen so that you can easily understand. A high power laser diode, which is in the infrared laser, this is 8.808 micrometer, or this is about 808 nanometer. I put everything in nanometer so that it is easy for you. This has a wavelength of 808 nanometer. Such a laser diode is very common. One such a thing is available for your 5G communication in your house. You can easily see this laser there. You cannot see, it's infrared, but they use this laser. Now, in this one, the cavity length, the length of the resonator is just 1 millimeter. Since the length of the cavity is 1 millimeter and the wavelength of light is 808 nanometer, in such a small length, it is capable of sustaining, supporting 2500 modes. That means it will allow so many frequencies come together, compete together. That is the first thing. All these modes are called resonance modes, and this wave, this particular standing wave pattern, since they are along the Z direction, we say this is the Z direction, this is the longitudinal direction. Why we say the longitudinal direction? You can immediately see from this graph, from this picture. See, laser is coming in this direction. The wave pattern, mode pattern are also in this same direction. That is why we say these are longitudinal mode patterns or longitudinal frequencies. Now, all these longitudinal cavity modes are allowed modes. Next step. In this particular example, the laser, when it operates, it is going to operate with amplification over 3 nanometer. Remember, some time ago, in one of the earlier lecture, I told you about amplified spontaneous emission. Now, recall that one. I can say this particular laser, if you pump it very hard, even without any kind of resonator mirror, will produce amplified spontaneous emission over a bandwidth of 3 nanometers. That is all what it means by gain line. Maybe I should repeat this one. Gain means light gets amplified. When it gets amplified, we say it has got a gain. And in this case, in this typical example, this particular laser has the property of producing amplified spontaneous emission or gain over a small bandwidth of 3 nanometer. Now, go back into this one. When you keep this one, this laser in a cavity of 1 millimeter, even then it is capable of supporting 10 longitude modes. Within this 10 longitude mode, some of them only can compete. I give this very good example. You must follow the first diagram. On the left side, the gain of the medium is given in the red line. You have a series of lines. These are all called the cavity modes, longitudinal cavity modes, which means all of them are allowed modes. But out of that, only those at the midpoint, at those 5 of them marked with the red line, they have amplification, they have the gain. Because of this one, you will be able to get a laser in those 5 of them only. That means oscillation threshold is allowed in the next one. In the diagram you can see oscillation is possible, laser action is possible only in those 4 longitudinal modes. I give an example, then you will be able to understand. Imagine there is a new business opportunity. The government announces any Indian can take a stake for solar power generation in Kamudi. Perhaps you should know, in the southern part of Tamil Nadu, there is a big solar panel factory to give power to Tamil Nadu electricity board. It is there now. Before they start operating, they would give an open announcement. Any Indian can bid for this one, start an industry. Imagine, I know how this solar energy works, so I will apply for it. Tata also knows this one and they also will do this one. Godrej also we know, they also will bid for this one. Then the government will say all the 3 of you bid for it. Who will win the race? I will be the first one to be kicked out because I don't know how to run the business. I know how solar power works, but I don't know how to do the business. I can manufacture, I can understand, I can explain, but I don't know how to do the business. So I will be kicked out. Out of the 2, Tata and Godrej, they will be a stiff competition. Out of the 2, eventually, let us imagine Tata has much better experience, so they will win the race. So you will have solar power production only by Tata. Keep this in mind. Now come back to the graph I have shown on the right side. You see the green line, a curvature like this one, that represents the gain medium. That means this is the business venture. The government gives so much encouragement and government says you will get enormous money, so much profit will be there. This is the gain medium in this particular business. Next line. You see so many straight lines, all these things are eligible Indians who are allowed to participate. There is no discrimination. Anybody who is an Indian can participate. But next, look at this one. After some time, when 3 of us participate, me, Godrej and Tata participate, look at this one. Let us say 5 of us, 5 or 10 of us are participate. You will see the only 5 of them will remain for 6 months or through 2 or 3 years to compete in the field. Even then, the company which is at the midpoint, like I said Tata, which is the highest gain compared to the other 2, they will grow in business faster, stronger than all the other 4. I repeat, there are 5 of them allowed to take a business. Out of them, whoever got the business experience, whoever got the manpower, only he will grow faster and faster. Since he has taken over the business, I will be kicked out automatically. Nobody will be kicking me out. I will slowly come out because I will be incurring loss. I will come out. This is exactly what happens in the laser process. After understanding all this one, you will see if we calculate the total bandwidth of the laser that comes out with after following all this competition will be 0.3 nanometer. Remember, we said the gain bandwidth is 3 nanometer. What comes out as a laser is 0.3 nanometer, which means the purity has improved 10 times more, or the coherence has improved 10 times more after doing all these resonator mirrors, pumping, everything put together. After all this engineering, you are able to get a laser at 808 nanometer with the spectral width of 0.3 nanometer, spectral purity of 0.3 nanometer. This makes this particular laser very, very coherent, and that is why you are able to use this one for your optical communication purposes. All the lasers. I have taken only a diode laser as an example. All the lasers follow this kind of pattern. What is important here is most of the commonly available lasers are multi-longitudinal mode lasers, because it is very difficult to allow only one single mode to operate, maybe 3 modes, 5 modes. Under that condition, it will be a laser with 3 or 4 mode. Again, going back to the same example of solar power panel, I said initially Tata will be the whole monopoly for laser, for solar power. But after some time, he also will get fed up, or he will get saturated. He may not be able to reach all the people. Take for example mobile. You have only 2 or 3 stakeholders now, because not one person cannot reach all the people. So 3 or 4 people provide our communication, cross communication techniques. So we can choose any one of them. In a similar fashion, usually in all the commonly available lasers, you will have 3 modes or 5 modes or 10 modes. Remember, greater the mode, lesser the purity. For special applications like holography, which I have mentioned here, holography, you need very, very pure laser, or it should be very coherent than others. Then only you can get a very clear holographic image. For that, we specially prepare single longitude mode laser. This needs additional process. One such additional process is introducing a Fabry-Perot ettalon, which is a very narrow, which is a parallel plate mirror facing each other with high reflectivity at that particular wavelength, high reflectivity of 100% and 98%, so that light which has gone inside will be able to go back and forth, allowing only one mode to survive in the competition, and that mode alone will be able to come back into the main laser process, and then you can get a laser of 1 kilohertz spectral width. This is the kind of laser, very, very pure laser, which is used for detection of very recent, very major achievement like a gravitational wave detection. You know, Einstein predicted gravitational waves somewhere in 1920 or 30, I do not remember. Until for the last 100 years, people were not able to check whether what he said is right or wrong. We were looking for a proper instrumentation for this one. Finally, it was a laser. One such laser is the single mode, single longitudinal mode, frequency stabilized laser, which proved to be the only solution for detecting gravitational waves. I mean, the gravitational wave is something, a wave which came from a distant galaxy. Somewhere in the two black holes are colliding together and they produce a shock wave, which we were able to detect using this kind of extremely pure lasers. We will continue in the second part more about transverse mode, and then we will see more about different resonator designs one after another. We need 2 or 3 lectures to understand the full implication, full purport of the resonators in the properties of lasers. We will see you one after another. Thank you very much.